Hello guys, welcome back to my YouTube channel. This is Namita from Information Science and Engineering Department studying at Sri Venkateswara College of Engineering. So the topic of today is process management and process scheduling. Contents of this video is introduction to process management and scheduling, what is a process states, process control blocks, process scheduling and its types, that is FCFS, SJF, RR, priority scheduling, process synchronization, mutual exclusion, deadlock, memory management, memory allocation, conclusion. Introduction to process management and scheduling. In the world of computer systems, processes are the building blocks that make everything run. They are the programs and applications that we use every day, from web browsers to video editing software. A process is simply an instance of a program that is currently running. However, managing these processes can be a complex task, especially in large-scale systems with many users and applications. That's where process management and scheduling come into play. These are the techniques and algorithms used by operating systems to manage and prioritize processes, ensuring that each one gets the resource it needs to run efficiently, from determining which process should run first for allocating memory and managing input-output operations. Process management and scheduling are critical components of any modern operating system. What is a process? A process is an instance of a program that is being executed by the operating system. It can be thought of as a container that holds all the information necessary for the program to run, including the program code, data, and resources such as memory and CPU time. Processes are fundamental to the functioning of modern operating systems, as they allow multiple programs to run simultaneously without interfering with each other. The operating system manages the execution of processes, allocating resources and scheduling them to run on the CPU according to a set of rules. Process states. A process can be in one of several states, including new, ready, running, waiting, and terminated. When a process is created, it is in the new state. In this state, the operating system allocates resources such as memory and CPU time to the processor. Once the resources has been allocated, the process moves to the ready state, where it waits for the CPU to execute it. When the CPU selects a process to run, it moves from the ready state to the running state. While in the running state, the process executes its instructions. If the process needs to wait for some event such as input, output, or a resource allocation, it moves to the waiting state. Once the event occurs, the process moves back to the ready state. Finally, when the process completes its execution, it moves to the terminated state. Process control block. The process control block, that is PCB, is a data structure used by operating systems to manage processes. It contains important information about each process, such as its current state, priority level, memory usage. The PCB plays a crucial role in process management, allowing the operating system to efficiently switch between processes and allocate resources as needed. By keeping track of each processor's status and resource requirements, the operating system can ensure that the system runs smoothly and without any errors. Process scheduling. Process scheduling is a critical aspect of operating systems that ensures efficient use of system resources. It involves deciding which process to execute next, how much time it should be allocated for execution, and when it should be preempted. Through this process scheduling, the operating system can prioritize certain processes over others based on their importance, allocate resources fairly among competing processes, and prevent resource starvation. Without proper process scheduling, the system may become unresponsive or inefficient, leading to poor user experience and decreased productivity. Scheduling algorithms. Scheduling algorithms are a crucial part of operating systems and determine how processes are managed by the system. There are several different types of scheduling algorithms used in modern operating systems, each with its own advantages and disadvantages. One type of scheduling algorithm is first come first serve, that is FCFS scheduling, which prioritizes process in the order that they arrive. While this approach is simple and easy to implement, it can lead to long wait times for processes with longer execution times. Another type of scheduling algorithm is shortest job first, that is SJF scheduling, which prioritizes processes based on their expected execution time. This approach can improve overall system performance by but requires accurate predictions of process execution times. First come first serve FCFS scheduling. First come first serve scheduling is a simple scheduling algorithm where the processes that arrive first is executed first. The scheduler maintains a queue of processes waiting to be executed and executes them in the order they arrive. This algorithm is easy to implement and ensures fairness as all processes are executed in the order they arrived. However, FCFS scheduling has some limitations. It may not be the best choice for systems with long running processes, as it can lead to long waiting times for other processes in the queue. Additionally, if a high priority process arrives after a low priority process has already started executing, the high priority process will have to wait until the low priority process completes, leading to poor response times. Shortest job first SJF scheduling. Shortest job first scheduling is a non-primitive algorithm that schedules processes based on their burst time, which is the amount of time required for a process to complete its execution. This means that the process with the shortest burst time will be executed first, as it is expected to complete quickly and free up resources for other processes. SJF scheduling can improve overall system performance by minimizing the average waiting time and turnaround time of processes. However, it requires knowledge of the burst time of each process, which may not always be available. Additionally, it may lead to starvation of process with longer burst times if they are constantly being preempted by shorter processes. Round robin RR scheduling. Round robin RR scheduling is a CPU scheduling algorithm that assigns a fixed time unit called a time slice or quantum to each process in a circular order. Once a process has used up its allotted time slice, it is preempted and moved to the back of the ready queue, allowing the next process to run. The advantage of this algorithm is that it provides fair allocation of CPU time to all processes, preventing any one process from monopolizing the CPU for an extended period of time. However, the disadvantage is that the time slice must be carefully chosen to balance between responsiveness and efficiency, as too short a time slice can lead to excessive content switching and overhead, while too long a time slice can result in poor response times for interactive process. Priority scheduling. Priority scheduling is a process scheduling algorithm that assigns priority to different processes based on their importance and urgency. The operating system then schedules the process in order of priority, with higher priority process being executed first. This type of scheduling can be completed quickly, or it is useful in situations where certain processes need to be completed quickly or have higher priority importance than others. For example, a real-time system may prioritize critical process over less important ones to ensure that they are completed in a timely manner. Process synchronization. Process synchronization is a critical aspect of operating system design that ensures multiple processes can be accessed shared resources without interfering with each other. Without proper synchronization, processes can overwrite each other's data or cause deadlocks, leading to system crashes and instability. Various synchronization techniques can be used to achieve process synchronization, including semaphores, monitors, and message passing. Mutual exclusion. Mutual exclusion is a fundamental concept in operating systems that ensures that only one process can access a shared resource at a time. This is achieved using locks and semaphores, which act as synchronization mechanisms to prevent race conditions and data inconsistencies. Locks are binary variables that can be either locked or unlocked. When a processor wants to access a shared resource, it is must first acquire the lock. Semaphores are similar to locks but can have integer values greater than 1. They are used to control access to a pool of resources rather than just a single resource. Deadlock. Deadlock is a situation in which two or more processes are unable to continue executing because they are waiting for each other to release resources. This can occur when there are limited resources and multiple processes require them simultaneously. There are several techniques that can be used to prevent deadlocks, such as resource allocation graphs, Banker's algorithm, and times out. These techniques involve careful management of resources and ensuring that processes do not hold onto them indefinitely. Memory management. Memory management is a critical component of any operating system. It involves managing the allocation and deallocation of memory to processes, ensuring that each process has access to the necessary resource to execute efficiently. The operating system uses various techniques to manage memory, such as paging, segmentation, and virtual memory. These techniques allow the system to optimize memory usage and improve overall system performance. Memory allocation. Memory allocation is a crucial aspect of process management in operating systems. There are various techniques used for memory allocation, such as contiguous allocation, non-contiguous allocation, paging, and segmentation. Contiguous allocation involves allocating a block of contiguous memory to a processor. Non-contiguous allocation, on the other hand, allows a processor to be allocated memory in different locations. Paging divides memory into fixed-size blocks called pages, while segmentation divides memory into logical segments. Conclusion. In conclusion, process management and scheduling are critical components of modern operating systems. By effectively managing process and allocating resource, these systems can ensure optimal performance and responsiveness for users. However, as we have seen, there are many challenges inherent in this process, from preventing deadlocks to ensuring fair allocation of resources. As technology continues to evolve, new approaches and solutions will be needed to address these challenges and ensure the continued success of our operating systems. Thank you.